Okay, so we got the problem set for week 9. Okay, so the first problem is find the Maclaurin series for e to the power. Let me pull up the problem set. I forgot. Write the Maclaurin series for f of x, function f of x equals e to the power ix. Okay, so basically, let's expand into a power series first. Centered at x equals 0. So as you can see here, f of x, f0, blah, 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 blah. And you know there's a little pattern right here going on. All right. So the next thing to do is find all the derivatives of each one. So f prime, double prime, triple prime. And then evaluating the derivatives at x equals 0 to get the coefficients. So f0 is 1, f prime 0 is I, f double prime -1, triple prime -I, quadruple prime -1. Therefore, plugging it in, everything in, you get 1 plus I to the power I times x minus half x squared minus 1 over 6x cubed plus 1 over 24x4. Originally, I put a negative here, but I saw David's explanation and it was actually a positive. So got that checked. And I just simplified these out. They were originally factorials. I just, solved them out. It was 2 factorial, 3 factorial, and then 4 factorial. Yeah. All right, so now for 1B, we are grouping real and imaginary. All right, so grouping them, got the reals and the imaginaries. Real parts are just without the imaginary I, imaginaries with the I's. So the real power, we notice, has even powers, and the imaginary part has all the odd powers. And so there's a famous Euler's method one called e to the power ix equals cosine x plus I sine x, which is important because this is going to help us for C. The trigonometric correlation here is actually very important. I actually found this really interesting. But yeah, I even broke it apart to make it make sense. Cosine x is all the reals. Sine x, I think I'm missing the I. No, it's just sine x, yeah. Yeah. Sine x is all the imaginaries, basically. Cosine x plus I times sine x. Okay, so for 1C. All right, so Euler's formula, E I times pi equals cosine included in pi, so cosine pi plus I times sine pi. So cosine pi we know is -1, and sine pi equals 0. So this is easy because I times 0 is 0. -1 plus 0 is obviously -1. Therefore, e to the power I times pi equals -1. This is all able to be solved because of Euler's formula. It's all correlated. Okay. So for number 2, I kind of did it 2 ways, but I'll explain. So estimating far the car moves the next second, using the second degree Taylor polynomial. So I'm just paying time t is st, because that's kind of like the more seen way to do is have it as st. Okay, so st equals s0 plus s prime 0, and then s double prime 0 over 2 factorial. I kept it in the factorial form this time compared to other problems to make more sense. So 20 is given. That's the speed. So that's going to be the prime, just prime. Acceleration is double prime. And then I forgot what triple prime was. That was also something we learned, but I forgot. But double prime acceleration, single prime is speed. So in this case, I kind of assumed for the first case that there is no acceleration going on. It's just 0, so it's 20 meters. Counting in the acceleration, I remember it was, for acceleration, it came out to 20 plus 1. Excuse me. 20 plus 1, so it'd be 21 meters, counting acceleration. So, let me read the question. Would it be reasonable to use this polynomial to estimate the distance traveled during the next minute? Okay, it really depends. So, let's say the speed and acceleration remain constant over the next minute. In short times periods, yes, this is pretty accurate within that minute. But however, if the speed or acceleration changes significantly, it may not be as accurate. But real world scenario, probably estimating the distance traveled over a minute, speed, acceleration, taking into factor. Obviously going to need more accurate and complex equations and models considering changes in speed and acceleration. But obviously that's not the point of the problem. I'm just saying, like, hypothetically. So for 3, I kind of overcomplicated this at first going through it the first time, but the second time I did it made a lot more sense. I was really overthinking it. So expected average for a point. Okay, expected series and determine the expected number of tosses. Differentiate. Oh yeah, it was the hint that really helps. Okay, so consider this right here: 1 plus a geometry series, 1 plus half squared, half cubed, and the sum of a geoseries is S equals 1 over 1 minus R. So the first thing I did was differentiate it. I did the differentiation through the power rule, and then I got to 1 over 1 minus R squared. And couldn't figure out what the R was at first, but it was literally right there in the half. And so R is half. So using this equation right here, got from differentiation, plugged it in, I got 4. So valuing series, it's 4. Expected number of tosses, I just put it back in normal S. 1 minus R, 1 over 1 minus R, 1 over half equals 2. So expected number of tosses is 2. Differentiated, 4. Yeah, that's it.